Okay, so we are now in week number 7, and we are talking about binary arithmetic. That is the topic for this week. So we are starting to get into things now. We've done a lot of the basics with this course. Now we're going to start getting into things where we can actually build circuits that are actually kind of useful. They do specific tasks. Grab my... Oh, dang. Grab my pen here. Okay, so we can create circuits to add and subtract binary numbers together. Understand how to accomplish this. Let's first look at the process of how we add 2 bits together. So just 2 regular bits. So it's basically 4 rules that you need to know for adding 2 individual bits together. The first one, the 0 plus 0. So if I have 0 and 0, that gives me 0. That's the rule for that one. If I have 0 plus 1, that gives me a 1. If I have a 1 and a 0, that also gives me a 1. Okay, that's this guy here and this guy here. And then the tricky one, if I have a 1 and a 1, what does that give me? That gives me a 0 with a carry of 1. That basically gives me a 2. So we call that a 0 with a carry of 1. We're going to call that a carry out. So the result is 0 with a carry out of 1. Okay, so that looks a lot like we would normally do our regular decimal adding that you're all very familiar with. Okay, so if we wanted to put that in the form of a truth table, it would look like this. So 0 and 0 gives us a 0 with a carry of 0. 0 and 1 and 1 and 0 both give us a sum of 1 with a carry of 0. A 1 and a 1 gives us a sum of 0 with a carry of 1. Now what you'll probably notice here, what does this look like? This truth table right here, what does that look like? This looks like the truth table for XOR, the exclusive OR. What is this like? What does this look like? This looks like the truth table for an AND. Okay? So basically we can say that if we have these two things, we're basically using an exclusive OR and an AND to create these truth tables. So we can create what we're going to call a half adder circuit for adding 2 individual bits together, and the result of this is going to be a sum and a carry out. Okay, and this is going to be lab number 7, part A. We will build this circuit in Tinkercad, and it will look like this. So we have input A and input B, so here and here, and we will build and test this. We will test all these different combinations, and what you will find here is it will look just like we just had. So our sums are going to look like this. So you'll get your LED that indicates sum will come on for those combinations. Your LED for carry out will come on for only this last combination down here. You'll get a truth table that looks like that. Okay, so this is called the half adder circuit. And it adds 2 bits together. Alright, so that is the half adder. It can be represented in block form diagram like this. So input A and input B, they go into the half adder, and you get a sum and a carry out like that. We'll use these block diagrams when we make some more complicated circuits in a little bit. The half subtractor is the next one we're going to do. The general rules for this one: 0 minus 0 yields 0. 0 minus 1 gives us a 1 with a borrow of 1. Okay? So if you have 0 minus 1, your result is going to be 1, and you are going to borrow from this column over here. So you have to borrow 1 from this column over here to make that operation happen. Okay, just like we would borrow if we were doing regular math. If we had 16 minus 8, we would say this gives us an 8, but we have to borrow this 1 from over here. This now becomes a 0, and that is our result. Okay? It's the same concept here. 1 minus 0 leaves a 1 with no borrowing, and a 1 minus 1 gives us a 0 with no borrowing. So this is the only case here that's kind of weird. We have that borrow going on here. So the truth table looks like this. So once again, we have a difference and a borrow. This one here looks like an XOR, and this one here looks like an AND. If you took the A, but instead of A, you made this A bar, then we would have one 0. So the only combination that shows up is this one here, and that is what gives you your 1. So if we use A bar instead of A, we can use that as an AND gate. Okay? So we have what we call the half subtractor. This is going to be Lab 7 Part B. The result is going to be a difference and a borrow. And our circuit looks like this, very similar to the half adder. The only difference here is we have now added this inverter in here. So that gives us, we had A here, now we have A bar over here instead. Okay, so our difference, that's the XOR function. And the borrow looks like that. So the difference light comes on for difference. The borrow light comes on when we actually have to perform a borrow operation. So the half subtractor subtracts 2 bits. Subtracts 2 bits, B from A. Okay, so we can create that circuit as well. We will test that out in the lab in Tinkercad. It can be represented like this. So A and B go in, we half subtract, we result in a difference and a borrow. Okay, so that is the half subtractor. The full adder. If you want to add more than a single bit together, you can build a table that will look like the one we're about to do here. So you have to consider if the bits are, basically which column are the bits in. Are they already bringing in a carry from the previous column? So when we say that, if we had, for example, we're going to add these together, we need to think of everything here in terms of, we are going to look at just this column here. So let's do an adding operation on this. So first of all, we have what we call a carry in. And then we have a carry out from this operation. So we have a 1 and a 1. First of all, do we have a carry in? In the very first column, we never have a carry in. Okay, so we do not have that. So carry in is going to be 0. The carry, so then we have our sum. Sigma represents sum. So the sum, we know a 1 and a 1 gives us a 0 with a carry out. So we have a carry out. We'll represent that right here. So we look at this column. Do we have a carry in? Yes, we do. We have this 1. It was a carry out from the previous column. So we have a 0 and a 1, which gives us a 1, and then we have to add the carry into that. So a 1 and a 1 gives us a 0 and a carry out. And we consider these. A 1 and a 0 give us a 1. We add the carry in, which is another 1. A 1 and a 1 give us a 0 with a carry out. And we basically have a 0 and a 0 here. 0 and a 0 give us 0. Add the carry in, which yields a 1 with no carry out. And then if we wanted to keep on going here, 0, 0, and 0. And you can see we just keep on going with zeros after that. So basically this is our result right here. I didn't give myself a lot of space to do this. If you want to just verify this math right here, that is 5 plus 3, and the result is 8. Okay, so you can see this is basically using, this is creating a full adder, and one of these can be made for each individual column, and you can just string together these adders for as many as you need, one for each column. You're just considering a carry in and a carry out for each. Okay, and then we can add up huge binary numbers together just by repeating that operation. So this is what our table looks like. Okay, so we have the A and B, we have the carry in, we have the resulting sum, and the resulting carry out. Representing it graphically, you can build up as many of these as you need to string together. So basically, A and B come in. You have the half adder. You have the sum result of this and the carry out. And then you take the sum as this, and you put that as the second input on another half adder, where you're using the carry in, and then our resulting sum, and you're adding those together. The result you get from that is your sum. And then you're taking, if you have either the sum or the carry out, these ORed together produce your resulting carry out. To put that in a circuit diagram, looks like this. Now you will notice here, this is basically a half adder. And this is basically a half adder. Okay? So this is basically A and B. This is our resulting sum. This is our carry in. And these are our carry outs coming together. Okay? And this will basically produce these results here. I believe that's right. Okay, and this is part C of the lab. That is producing the full adder on our board. And then the final thing we're going to do in the lab, and the final thing we're going to do in this lesson, the 4-bit parallel adder. This is capable of adding a 4-bit number to another 4-bit number. The result can be as large as a 5-bit number. So this will allow us to add these two numbers together. Okay. Now the way this works, we actually have a chip that does this for us. We're going to use the 283 chip. We actually have this in Tinkercad as well. So the way this is laid out, you will see we have power, we have ground. This is a 16-pin chip, so ground is now on 8, power is on 16. And the inputs going to this, we have A1, A2, A3, and A4. So what that represents, if we have two numbers being added, this is basically what you have. This C0 over here, that is the carry in to that. Okay, so that is how everything connects together. The reason we have a carry out, or sorry, a carry in this C0, if you wanted to do two 8-bit numbers together, you could use two of these together, and basically the C4 from this one, you could plug into the C0 of another one, and do that addition like that. So basically in block diagram, this is how we do that. So it's basically a full adder, another full adder, another full adder, and another full adder. And it's producing these 5 bits down here. For our purposes, this C0, that is going to be low. So we are just going to tie that to the 0 volts. So this is our circuit that we will do here. Now the way that they show this here, they have a 8-position dip switch. So they're basically breaking this in two. So this gives you 4 bits. This gives you 4 bits. It's probably the way we'll do it in our lab. We can do 2 separate switches. Just to make things easier to follow, we can do it like this, on 2 separate switches. But basically we have, you put in a number here, you put in a number here, it adds them together, and you will get a combination of lights that will basically light up according to what the result should be. So that is the 4-bit parallel adder. Okay? It's going to ask you to go through and verify all these numbers. So if you input 5 and 5, you should get a 10 as a result. In hex, that is 10 is A. Should give you that. Okay. So that is binary arithmetic. So we are actually building a little calculator with this, which is kind of neat. So something that actually does something useful. So that is the lab and the lesson for this week. A couple other things we're going to talk about this week is kind of why are we actually learning all of these things? What is the use behind all of this? Where does it lead? So here is our program laid out with all the courses. So you are in term 1 right now. There's these things here. This is digital fundamentals. So this course leads into ERT207 programming, which will be in the winter. After that, you go into PLC Part 1 and PLC Part 2. Okay, these are all connected, they're all prerequisites for each other. So what is a PLC? So in the lab right now, we do stuff like this. We make combinational logic circuits on a breadboard. When you get into the PLC lab, you start doing very similar things, but you do a more industrial version of it using a PLC. So you're basically making logic circuits in a PLC to control a machine. Okay, so in the lab, we are making things that look like this. When you start doing PLC, we'll be doing what we call ladder logic. which looks like this here. Okay, so this is basically writing code in ladder form, ladder logic, because guess what? It looks like a ladder. And this is how we write machine code to control industrial machines. Alright, so kind of three different generations here. We have relay, so using physical devices such as limit switches. And that runs a light, and that's basically just power flow. We have ladder logic, and we have a logic gate. So all three of these things are basically doing the same thing. This is basically saying if limit switch number 1 is on, limit switch number 2 is on, the light comes on. This is saying if input A is on and input B is on, output X comes on. And this is saying if input A is on and input B is on, output X comes on. This is all written the same way. Likewise, this is an OR gate. If A is on or if B is on, turn on output X. Okay? So you need to understand how this stuff works before you can understand how this stuff works. So this is why we're learning these things right now. They get more complicated, and as you can see, this much more complicated to look at than this, but that means exactly the same thing. If A and B is on, or if C and D is on, turn on X. If B is not on, turn on X. And this is basically our safety circuit that we do in the safety class. Where if you push the button here, you get X to come on. Feedback up here holds that on, which seals this in. That stays on until you push that button. That is basically the same thing as we're doing here with ladder logic as well. This is a feedback or a sealing circuit. Okay, so if we know how to do those types of things, we can control a little machine like this, where we say, I place a box over here, that makes this switch come on, box travels down the conveyor until I hit this switch, and then my red light comes on, green light runs. Green light's on whenever the motor's running. Whenever I want the conveyor to run, I turn on this motor. I have lots of different start and stop buttons that control its operation as well. This, you need a PLC program to run this, and this is the core of what you're trying to learn here. This is what people do professionally to try to do things like this. Okay, so this is what we're working towards, being able to program little machines like this. Okay, so let's take a little break here, then we'll do a couple of practice problems.